Okay. Good day, viewers all over the world. Welcome to Troidel online class. So we are going to continue from where we stopped on matrices. Now, in our last class, I introduced matrices and I defined a matrix as a set of real or complex numbers arranged in rows and columns to form a rectangular array. For instance, when you have matrix A 20 minus 1 4. So we said that this is a matrix. This is arranged in rows and columns. And in this case now, I said if you want to name a matrix, it is row by column. We use this multiplication sign to represent by. So matrix A is how many rows do we have? 1, 2. And how many columns? 1, 2. So matrix A is 2 by 2 matrix. So this is how we arrange a matrix. This is how we arrange a matrix. So last week also we talked about a row and column matrix. I said a matrix that has one row is called a row matrix, and a matrix that has one column is called a column matrix. We talked about equality of equal matrices. That is, two matrices are said to be equal if they have the same formation. 2 by 2 to 2 by 2, 3 by 3 to 3 by 3, 4 by 1 to 4 by 1. Then we discussed about addition and subtraction of matrices. So we try to look at how we can combine two or more matrices. We have done that, and how we can actually subtract a matrix from the other. Then I also introduced multiplication of matrices. So we talked about scalar multiplication and matrix multiplication. Under scalar multiplication, if you have a matrix A, say A, B, C, D. So if you have 3A, 3A simply means that you are going to use this scalar. This 3, you use this constant or scalar to multiply all the entries that you have here. But in case of matrix multiplication, is when you have two matrices, and I gave us the condition on how to multiply two or more matrices. I said if you have a matrix m by n and you have another matrix n by say p, the condition that must be satisfied for two matrices for multiplication of two matrices is that the column of this first matrix must be equal to the row of the second matrix. That's what we said in the last class. That is, if this is 2 by 3, you have matrix 2 by 3, and you have 3 by 4. Is it possible to multiply these two matrices? Yes. Why? Because the column of the first matrix is equal to the row of the second matrix. That shows that it is possible. That shows the possibility. Then the results that you are going to get after everything, this will be the results. So if you use 2 by 3 matrix to multiply a 3 by 4 matrix, your result will be 2 by 4. So in this case, generally now, if you use m by n matrix to multiply n by p, the result that you are going to get will be what? M by p. So that is what we discussed in our last class, scalar multiplication and matrix multiplication. Today, by the grace of God, I'm going to introduce transpose of a matrix. Transpose of a matrix. How do we transpose a matrix? That is, transpose of a matrix simply means the rearrangement of elements in a given matrix with rows and column interchange. So if you say transpose of a matrix, let's say we have a matrix A given as 1, 2, minus 4, 3. If this is a matrix A, what will be the transpose of this matrix? The transpose of A, denoted as A superscript C, simply means that we are going to interchange row to column. That's the simple interpretation of transpose of matrix. That is, the first row now becomes first column. The second row will become second column. So this is the meaning of transpose of a matrix. If you have a matrix 2, 1, 3, 4, 6, 8. So if this is matrix B, you have a matrix B, and this matrix 1, 2, 3. This is 3 by 2 matrix. Because how do we name a matrix? Number of row by column. So if the B is 3 by 2 matrix, what will be the transpose of B? B transpose will now be first row to first column, second row to second column, then third row to third column. That will be 2, 1, 3, 4, 6, 8. So when we transpose a 3 by 2 matrix, we are going to get 2 by 3. because the number of rows have reduced to 2, while the number of columns have increased to 3. So this is all about transpose of a matrix. So if you want to transpose a matrix, just interchange row to column. That is the implication. And there are some properties. We are going to make use of this transpose of a matrix when we get to how to find the inverse of a matrix. So let's talk about special matrices. I want to talk briefly on special matrices. That is, these are the matrices that it is expected that we are all familiar with. The first one is called a square matrix. A square matrix. A square matrix. A square matrix is a matrix of order. A square matrix is a matrix of order m by m. That is, when the number of rows is equal to the number of columns, then such a matrix is referred to as a square matrix. For instance, let's say A, which is A11, A12, A21, A22. In this case now, this A is a square matrix. Why is it a square matrix? Because the number of rows, there are 2 rows there. The horizontal movement is row, while the vertical is column. So how many rows do we have here? 1, 2. This is 2. By how many columns? 2. So this is a 2 by 2 matrix. So when we have m by m matrix, that simply means that the number of rows is equal to the number of columns. We can have 3 by 3 matrix, we can have 4 by 4, we can have 5 by 5, etc. So when we talk about square matrix simply means that the number of rows that we have must be equal to the number of columns. Not all matrices are square matrices, but when we have something of this format, then we call it a square matrix. Another special matrix that we talk about is called the diagonal matrix. Diagonal matrix. So that will be the second one. So when in case of diagonal matrix, of course, diagonal matrix is also is a square matrix. It's a square matrix with non-zero elements at the leading diagonal. For instance, if you have a matrix A, which is equal to 2, 3, 5, 0. In this case now, this matrix is a diagonal matrix. Why is it a diagonal matrix? This matrix is a diagonal matrix. Why is this matrix a diagonal matrix? Because we have non-zero elements on other part of the matrices except on the leading diagonal. Of course, when you have a rectangle, we talk about diagonal. This is the diagonal of a rectangle. There's another diagonal. But the first one from the left to right is called the leading diagonal. So in this case now, what we have here is the leading diagonal. So a diagonal matrix is a square matrix that has all the entries along the leading diagonal to be non-zero. But we can have entries. Every other entries will be 0. For instance, I can have 1, 0, 0. No, let me say 6, 0, 0. I can have 0, 7, 8. Then I can have 0, 0. No, 0, 7, 0. Then 0, 0, 8. Like this matrix B is also a diagonal matrix. Why is it a diagonal matrix? Every other element here are zeros except that of the leading diagonal. This is the leading diagonal. From left to right is the leading diagonal. So every other element will be 0 except that of the leading diagonal. So matrix A and B on the board is a typical example of a diagonal matrix. Diagonal matrix is a square matrix that has non-zero elements along the leading diagonal. So let's take note. Then we can also have the third one. We can have a unit matrix. Number 3. In case of a unit matrix is a diagonal matrix in which all the elements and the leading diagonal are units. That is, this is what I'm trying to say. So unit matrix is also a diagonal matrix. But the only difference is that in case of diagonal matrix, you can have any other value, any other digits. But in case of the unit matrix, it's 1, 1 that we have there. Along the leading diagonal, we have 1, 1, 1. So that's just the difference between a diagonal matrix and a unit matrix. In case of diagonal matrix, we can have any digits there. But in case of a unit matrix, it must be a unity, 1, 1, 1. So a diagonal matrix and a unit matrix has the same entries, except that in case of a diagonal matrix, the element along the leading diagonal could be any value. But in case of a unit matrix, it must be 1. So this is example of a unit matrix. Okay, we can also have a known matrix. A known matrix. A known matrix. This is the fourth property. In case of this now, in case of a known matrix, every element, every entries must be 0. Okay. In case of this now, all the entries must be 0. 0. Everything must be 0. Then the last special matrix that we are going to consider is called the triangular matrix. Triangular matrix. So this is the fifth special matrix that we talk about. In case of this triangular matrix, there are two types. We have upper triangular matrix and we have lower triangular matrix. So a triangular matrix is a square matrix in which all the elements above or below the principal diagonal are zeros. Okay. For instance, let's say A, matrix A. Let me introduce matrix A. Let me introduce matrix A as, let's say, matrix A, I have maybe A00, BC0, then DEF. If this is a matrix A, you realize that along this leading diagonal, principal leading diagonal, all the entries above here is 0. Let me give another example. Let's say matrix B. I have A, B, C, and I have 0, D, E, 0, 0, F. Matrix A, all the entries above the leading diagonal are zeros. Then matrix B, all the entries below the leading diagonal are zeros. In this case now, matrix A is called upper triangular matrix, while matrix B is called lower triangular matrix. So both of these matrices are triangular matrix. A is called upper. Why is it upper? Because all the entries above the leading diagonals are zeros. All these entries above. So this one is called upper triangular matrix. In this case now, it's also a triangular matrix. But in this case now, this triangular matrix is lower triangular matrix because all the entries below the leading diagonals are zeros. Okay. So we've considered the 5 special matrices so that we are expected to be familiar with. So I will just briefly make some statements about matrix operation and algebraic law. You see, under commutativity, on A plus B is always equal to B plus A. So that shows that addition of matrix is commutative when you have a matrix A and B. When you add the two together, so it is going to give us the same result. So addition of matrix is commutative. Then there's this other one. In case of subtraction, A minus B, will it be the same thing as B minus A? No, we don't usually get this. So that shows that subtraction of matrix is not commutative. When we look at matrix operation and algebraic law, I'm trying to make this general statement under commutativity. Commutativity. I'm trying to say that matrix addition is commutative. Matrix subtraction is not commutative in general. Then under multiplication, 3, AB, when you say multiply matrix A to multiply B, it's not always equal to BA. So the matrix multiplication is not commutative. Please note all this. That when you add two matrices together, you get the same answer. When you subtract one matrix from the other, it's not always, it's possible to get it, but it is not in general. It's not always equal to B minus A. The multiplication also, A times B, matrix A times matrix B, is not always equal to B times A. So in general, what we are trying to say is that matrix addition of matrix is commutative. Subtraction of two or more matrices is not commutative. Why multiplication also? Matrix multiplication is not commutative. So when we look at this other property, which is called associative property, that's when we have about three matrices. Let's say we have A plus B, then we now relate it with C. And same thing as we first have A plus B plus C. Under addition, it is possible. Under addition is possible. So addition of matrices is associative. Addition of matrices is associative. Let's note that. But under subtraction, would that be possible? A, B minus C. Under subtraction, it is not possible. So subtraction of matrices is not associative. Then under multiplication also, under multiplication, when we have AB multiplied by C, will it be the same thing as A multiplied by BC? Yes. So multiplication, matrix multiplication is associative. Matrix addition is associative, but matrix subtraction is not associative. Then we should also know that when we talk about distributive, distributivity, we should know that multiplication is distributive over addition and subtraction, and the converse does not hold. That is, when you have a matrix A multiplying matrix B plus or minus C, that is, it is always the same thing as matrix AB plus or minus BC, AC. This is what we are saying. That if you have a matrix A, then if you first add matrix B plus C, or you subtract matrix C from B, if now use A to multiply, we are going to get this. That simply means that multiplication under matrix operation, multiplication distributes over addition and subtraction. That is just the simple interpretation when we consider matrices and algebraic law. So we can check for all these statements. Just give a typical example, then you check. So now let me introduce determinants, which will be our last concept for today. Determinants. Determinants of a square matrix. You know, when I introduce special matrices, you realize that I only talk about square matrix. That is when the number of rows is equal to the number of columns. That's the example of a square matrix. So when I introduce special matrices, every example that I gave is example under square matrix. Is example under square matrix. So I want to talk about determinant of a square matrix. So how do I what do I do there? Under determinant of a square matrix. So under determinant of a square matrix, then what do I do? Just look at, if you have, let's say we have a matrix P, which is equal to A, B, C, D. This is a given matrix. So how do I find the determinant of this matrix? Of course, it's very simple. If you want to find the determinant of this matrix P, this is 2 by 2. We normally denote it as the symbol of absolute value. Just like when we talk about absolute value. The determinant of this will now be, you are going to use the leading diagonal to multiply each other minus this. This is how to find the determinant. That is A times D. I'm going to have AD minus B times C, BC. So this is how to find the determinant of a 2 by 2 matrix. It's very simple. But in case of 3 by 3, there are some additional things that we are going to do. So determinant can be found as algebraic sum in case of 3 by 3. If you want to find determinant of 3 by 3 matrix, so that determinant can be found as the algebraic sum of products of cofactors of elements in the first row and the respective elements. And of course, the determinant of a matrix has a lot of properties. The first one is that determinant is 0 for a consistent matrix. That is, it is possible to find determinant of a matrix and get 0. A matrix in which determinant is 0 is called a singular matrix. So when you find the determinant of a given matrix, and at the end of the day you arrive at 0, that simply means that that matrix is a singular matrix. And once it's a singular matrix, it does not have inverse. Singular matrices are not invertible. So you cannot find the inverse of a singular matrix. So anytime you are working on that matrices, and when you find the determinant of the matrix and the determinant is 0, that matrix does not have inverse. So when the determinant of the matrix is 0, that matrix is called a singular matrix. So another property is that when you interchange first row, a row or a column, we still get the same answer as the determinant. So these are some of the properties. Then why do we need determinant of a matrix? There are some applications of determinant of a matrix. The first one is that we use it for ranking of a matrix. So if you want to rank a matrix, we use the knowledge of determinant of a matrix to rank a matrix. It is used for classifying a matrix as singular or not singular. That is, if you want to know the nature of a matrix, that either the matrix is singular or not non-singular, we use the determinant to classify a matrix to be either singular or non-singular. Another application of determinant of a matrix is that it is used for determining the inverse of a matrix. That is, we are still going to consider the concept called inverse of a matrix. How do we find the inverse of a matrix? The knowledge of determinant is key, because once you find the determinant of a matrix and it's zero, that matrix has no inverse. So the last application is that it is used for simplifying simultaneous linear equations. That is, we can use the knowledge of determinant of a matrix to find simultaneous linear equation, system of equation, where you have 2 by 2 matrix, 2 by 2 equation. We can have three simultaneous equation involving 3 variables, involving 4 variables, and the rest. We can even use it for system of linear equations. So those are some of the applications. So let me take example now. I'm going to take example now. Let's example one. Under determinant of a matrix. Under determinant, the question says find the value of x for which 3 minus x, this is 9, minus 1 plus 2x is equal to 0. Of course, when I introduced determinant of matrix, I said we denote determinant of matrix P as this. And it simply means, and if this is 2 by 2 matrix A, B, C, D, it simply means that you multiply the leading diagonal minus the other diagonal. Okay? So in this case now, we want to find the value of x. So what do? We have to take the determinant. I will say 3 minus x multiplied by 1 minus plus 2x minus, into bracket, minus 1 times 9 minus 9. Of course, here is given as 0. So when I expand, I will have 3 plus 6x minus x minus 2x squared minus times minus plus 9 equal to 0. So here I'm going to have minus 2x squared plus 5x plus 12 equal to 0. That's what I'm going to get. Then I can multiply through by minus. I'm going to have 2x squared minus 5x minus 12 to be equal to 0. So the SCM is, this is 2 times 12, 24. What are the 2 factors of 24? That will be minus 8. I'm going to have 2x squared. This correct equation now factorize. Minus 8x plus 3x minus 12 equal to 0. So I do the grouping. 2x is common here. I'm going to have x minus 4 plus 3 is common. I will have x minus 4 equal to 0. This simply means that 2x plus 3, then x minus 4 equals 0. So from there now, we want to find the value of x. I'm going to say that 2x plus 3 equals 0, or x minus 4 equals 0. So 2x is equal to 3, or x is equal to 4. Finally, x is equal to minus 3 all over 2, or 4. And that will be the value of x that we are required to find. Okay? So that example is just example under 2 by 2 matrix. Now let's take another example where we have 3 by 3 matrix. Then I will use that example to explain. If A is equal to, how do we find the determinant of 3 by 3 matrix? If A is equal to 1, 4, 3, 6, 2, 5, then 1, 7, 0. The question now says determine the determinant of A. This is the symbol for determinant. So to find the determinant of A now, what do? Let's just do it this way: 1, 4, 3, 6, 2, 5, 1, 7, 0. So if you want to find the determinant of A in this case now, no, this is 3 by 3. 2 by 3 is very simple. Little diagonal minus the other diagonal. But to find the determinant of A in this case now, this is what you do. We are going to write plus minus plus on the first row. How do I get the plus minus plus? This one is the first row and first column. That's 1, 1. That is plus. This is first row, second column, 1 plus 2, 3. That's odd. It attracts negative sign. Then this is first row and third column, 1 plus 3. That's 4. That is even. So this is plus minus plus. Then this is what we now do. Look at it. We pick the first one. the first entry here, 1. So we now do, when we pick the first entry, this first entry is along first row and first column. So let's pretend as if we cover first row and first column. What do we have left? We have 2570. So we are going to write 2570 here. That is when we consider the first one here. Then minus 4. You know, I generated this plus minus plus automatically. Then this 4 is along first row and second column. So let's pretend as if we cover first row and second column. What do we have left? 6510. We have 6510. Then plus 3. This 3 is the first row, last column, the third column. So let's pretend as if we cover first row and last column. We have 6217. That is how to do it. If you want to find the determinant of 3 by 3 matrix, just write it out. Then along the first row or first column, but I decided to use the first row, put plus minus plus there. Then what do? Pick the first entry, first row. That first entry is along first row and first column. So once you pick the first entry, 1, write out the leftover. Come to the first row, second column, which is minus 4. Then pretend as if you cover the first row and first column. Write out the leftover. You come to the third one, which is first row, third column. Right? This in this case is 3 plus 3. Then pretend as if you cover first row and third column. You write out the leftover. Then from there now, we can then simplify this. So here I'm going to have 1 into bracket 2 times 0. You just use the normal method of finding determinant of 2 by 2. That will be 2 times 0 minus, that will be 0 minus 5 times 7, 35. Then minus 4 into bracket 6 times 0, that's the leading diagonal. 6 times 0 is 0 minus 5. Then plus 3 into bracket 6 times 7, it is this minus this. So 6 times 7 leading diagonal. 6 times 7 is 42. That will be 42 minus 1 times 2, 2. So here I'm going to have 1 into bracket minus 35, minus 4 into bracket minus 5, then plus 3 into bracket 40. So if I simplify, I'm going to get minus 35 plus 20 plus 120. So at the end of the day, we are going to have 140 minus 35. The determinant of A that we are looking for will now be, that will be 105. And that's how to find the determinant of a 3 by 3 matrix. So that's what you do if you want to find the determinant of 3 by 3 matrix. So that's simple. Or there's this other method. If you don't want to go through this first, then there's this another method that you can use when you want to find the determinant of 3 by 3 and the rest. It is called the Sarus rule. So after the Sarus rule, then I'm going to close for today. If you don't want to do it this way, we can go ahead and apply what is called the Sarus rule. It is called the Sarus rule. We can use Sarus rule to find the determinant of 3 by 3 matrix. Then how do we apply Sarus rule? So let's just do that. What is the value of A? A is given as 143, 625, then 170. So if you want to apply Sarus rule to find the determinant of this matrix, this is what we do. Sarus rule says that you write what you are given, 143, 625, then 170. Then if you want to apply this rule now to find the determinant of 3 by 3 matrix, then this is what you do. Once you write what you are given, you write what you are given. We are not going to repeat the first 2 columns. You repeat it. That is, I will have 161, then 427. That is what the rule says. Then we will now look for the leading diagonal. In this case now, we now have 3 by 5 matrix. It's 3 by 5. We still have 3 rows, but we have gotten additional 2 columns. So you now trace out the leading diagonal here. This is the first one, the first leading diagonal here. You trace out the leading diagonal. You find the value. That will be 1 times 2. That's 2. 2 times 0 is 0. Plus 4 times 5. 20. 20 times 1, 21. 21. Then you also have 3 times 6. 18. No, let's say 6 times 7. 3 times 6, 18. 18 times 7. 18 times 7 is 126. That's 126. That's what the law says. or let me write it stepwisely. So I'm going to say the first one is 1 times 2 times 0, so that it will be clearer, plus 4 times 5 times 1, then plus 3 times 6 times 7. Then once you find this, minus, you do the same thing here. Trace out the diagonal of this second one. This is the leading diagonal, then this is the other diagonal. You trace out the diagonal of the second one, we do the same thing there. That is 1 times, the first one will now be 1 times 2 times 3 plus 7 times 5, 7 times 5 times 1, 7 times 5 times 1, plus, then is 0 times 6 times 4. That's what you get. So if you simplify this, what do you get? This is 0 plus 4 times 5, this 20 plus 126 minus, let's simplify what you have inside this bracket. This will be 2 times, this will be 2, 1 times, this 6 plus 7 times 5, 35 plus 0. So if we simplify for that, what do we get? Is 0 plus 20, that's 1, this 146 minus 41. At the end of the day, we are going to get 105, which is the same thing that we got when we use the other method. So if you want to find the determinant of a matrix, of course, you can use the first method that I applied. That is, if it's 3 by 3, just put plus minus plus. Then you bring out the entries, write the leftover, you get your determinants. Or you apply this Saros rule. In case of Saros rule, just repeat the first 2 columns, then trace out the leading diagonal, the 3 leading diagonal, and the other, subtract it from the other diagonal. You realize that we arrive at the same answer. So I would love to stop here because of our time. We are going to continue from there in our next class. Thank you, and God bless you.